Hi there, I'm Colin and I'll be your narrator for today. In this module, we're going to learn how to differentiate composite functions using something called the chain rule. In Day 8, we learned how to recognize when a given function was a composite function, also known as a function of a function. For instance, consider the function y equals 2x minus 1 all to the power of 7. Here, it appears that 2x minus 1, a function in its own right, is nested within the function that raises everything to the power of 7. Therefore, the inside function f of x is 2x minus 1, and the outside function g of u is u to the power of 7. Here's another example. Consider the function y equals x squared plus 3, all square rooted. Here, the inside function is x squared plus 3, and the outside function is the square root function. For a given composite function, if we're able to explicitly identify the inner and outer functions like we did before, we can use something called the chain rule to differentiate the function. In particular, if we call the inside function u, then we can write y in terms of u. The chain rule then states that our derivative dy dx is equal to dy du times du dx. In other words, dy dx is simply the product of two simpler derivatives. Here's the common functional notation for the chain rule, which you may encounter in textbooks. Let's now use the chain rule to differentiate the composite function y equals 2x minus 1, all raised to the power of 7. We first identify the inner function u as the function 2x minus 1, as we had done earlier. This now means we can write y in terms of u, namely y equals u to the power of 7. The chain rule then states that our derivative dy dx is equal to dy du times du dx. So now all we have to do is calculate these two smaller derivatives and simply multiply them together. Since y equals u to the power of 7, dy du is 7 times u to the power of 6 using the power law. And since u equals 2x minus 1, du dx is just 2. Now our answer must be in terms of x, so switching u back to 2x minus 1, we thus have our derivative dy dx to be the following. Let's look at another example. Consider the composite function y equals x squared plus 3, all square rooted. We first identify the inner function as x squared plus 3, as we did earlier. This then means that we can write y as the square root of u. The chain rule then states that the derivative dy dx is equal to dy du times du dx. Since y equals u to the half, dy du is a half times u to the minus a half using the power law. And since u equals x squared plus 3, du dx is 2x. We then substitute back for u to obtain an answer in terms of x only, which gives us the following upon simplifying. Here's a final example. Y equals e to the power of x squared plus 1. Setting our inner function u to be x squared plus 1, y is therefore e to the u. In accordance with the chain rule, we differentiate y with respect to u and u with respect to x separately, and then multiply these two smaller derivatives together. Remember to make sure your answer is in terms of x only. Alright, time to pause the module and have a go at differentiating the following composite functions using the chain rule. As with the above examples, the technique involves first identifying the inner function u, and then writing y in terms of u. You then work out dy du and du dx and multiply them together in accordance with the rule. Remember to make sure your answer is in terms of x only. Here are the answers to the practice questions.